Right at year 12, I want to just go over a couple of things to do with photons so we can finish off this little subsection and get on to the last one on lasers. But firstly, I want to look at the number of photons. Now what we've met so far is that we have waves acting like particles, and Planck said that each one of those has got an energy which is equal to hf. Now, from what we know before, we can work out from wavelength and frequency the speed of light. And so we've got the tools to be able to work out the energy of the photon. The thing we've got to remember is photons quite often don't occur on their own. They occur in beams of light. And these beams of light quite often have a power associated with them. Now if you remember, power is energy per unit time. And so I'm hoping you can see that there's energy here and there's the energy of one photon. So if you've got a beam of light which has got a certain power, then we can get to the number of photons, using n, and then the energy of one photon divided by the time. Now quite often questions will say this is the power in watts. And what we've got to remember is a watt is joules per second, and so we will often take that this time is 1 second. So if we know the energy of a photon and we know it's the power of a light beam, we can get to the number of photons by dividing the power by the energy of one photon. And this comes up a lot, and it comes up when we're dealing with momentum of photons, which I want to go over in a second. And so if we know the number of photons, we know the energy of the photons, we can work out the power. The second thing I just want to go on to is that there is something called intensity. And intensity is the power per unit area. And quite often when we think about this might be to do with the sun. So the sun on a bright summer's day generally gives to the UK about 1,200 watts per metre squared of energy. And so if you think about solar panels, they're converting that energy, and so we can generate electricity. And so we know that a certain size will produce a certain power, and that will then allow us to generate a certain amount of electricity. The second thing I want us to look at is to do with momentum. And so photons have been found to have momentum. Now this is a strange thing to think about, because we think about the photon, we think about it being a wave, and we might think, well, light in general doesn't actually affect us. You know, when it hits us, we don't feel the inclination to move, but that's because we've got gravity acting on us, it's because we've got air around us, and these photons are going to give a very small force. But when you're out in space, that small force can end up having a massive effect. And so, because we know the wavelength, people came up with the idea that the momentum of a photon is given by h divided by lambda. And I might call that little p with a ph on it. Now that's important because if we've got something like a satellite with a solar panel on it, and it's being hit by these photons, and they have got momentum, this is going to be affected in some way. And so if you think about, just if we had a pea shooter and we're firing lots of peas at something, steadily that thing would start to move. So if it was a panel on a roller skate or something, we might see that over time that moves. It might not move very far, but it could have an impact on where it is in terms of its space. Now, we've got two processes that can happen. We can have things being absorbed, or we can have things being reflected. Now, we've got our photon, and we've got our solar panel, and this has got zero velocity. It will have zero momentum, but this will have momentum. And so beforehand, there'll be this momentum. If this photon gets absorbed, well, that momentum has got to go somewhere. And so what ends up happening is the solar panel ends up moving. And so the solar panel will end up having momentum of the photon. If things are reflected though, and so here again we've got our solar panel, maybe it's different in terms of material this time, or it might be something that's shiny. We've got our photon comes in, but if it gets reflected, it goes along the same path. Now, we've got to remember that momentum, because it's got velocity in it, is a vector quantity. And so this might be positive p, but this here would be minus p. Now, it's a bit difficult to show on here the way I've done it, but this has gone and hit this. This is now reflected back. And so the momentum before would be plus p. If that was stationary, then afterwards, this would have to equal minus p plus some other quantity. And if I take that minus p to the other side, then what we find is that this moves with a momentum x, which is 2 lots of momentum. The other way to think about this is to work out the change in momentum of the photons, which would be minus 2p, and then think about, well, if it's had a change in momentum, there's been a force exerted, and that force would be force per unit time, or would be to do with change in momentum per unit time. And then what we find out is that because of Newton's third law, if this is minus 2p, then this has to be plus 2p. And so we get this case here. Now, depending on the wording of an exam question, if it was absorbed, it would just be a straightforward transfer of momentum. If it's reflected though, we've got to make sure we include this factor 2. Now I'm going to set some exam questions for you to work on which might use some of these concepts, and then later in the week I will post some notes on lasers, and that'll be us aiming to finish this, and after Easter we'll see what we do in terms of maybe doing some prep for year 13.